Okay, let's get started. I think we're live, or we're probably very close to being live. I'm Lou Fulton. I'm co-director of STEPS here at ITS Davis, and it's great to see this great turnout today. I know most of you. I don't think I've met everybody here. We do have a couple of special guests today from Warwick University. I want to mention Nick Mallinson and Andreas Hofrichter sitting back there. Thanks for attending, guys, and it's great that you're here. We're very fortunate today to have a speaker who's also a good friend of mine, great speaker and a great expert on a wide range of issues around bioenergy. He's been doing this for a long time. His name is Lee Lind, Professor Lee Lind from Dartmouth, and I will give some of his very long resume. I won't give it all, but I wanted to say that I met Lee in 1994. So that's probably before some of you were born. Maybe not many. Maybe you were mostly born by then. And it was, at that time, I was a government working stiff. I worked at the Department of Energy. Lee was doing kind of what you do now. You were already a professor at Dartmouth by then. And there was something called Car Talk, which was an effort under the fairly young Clinton administration to get automakers and environmental groups around the table and figure out what to do about vehicles and climate change. So that was 1994. So this is not a new problem. And we were just commenting that it was a really interesting process. Lee was there as an expert, and there were a number of experts involved. I was there as a government person trying to keep track of what was going on, and I actually was building a model, which is one thing I like to do, around what the different groups were willing to consider in terms of alternative fuels and fuel economy improvements. And we were really hoping that there would be a grand solution that would then lead to U.S. policy on a range of issues around energy and climate. But in the middle of the process, there was the midterm election, which was basically the Gingrich revolution, and Newt Gingrich became Speaker of the House, and the automakers didn't care anymore. And the process, we went through with it. We came up with some plans, but nothing ever got implemented. So that was one of the less great outcomes, but there have been some very good outcomes since then, and we keep struggling along. Anyway, it's great to have Lee here today. He's at the Thayer School of Engineering at Dartmouth, and he's a Global Sustainable Bioenergy Project Leader, and he also runs something called the Enchi Corporation. I think you have a fourth thing, but one of them is that you're a husband and a father. I think that comes first. He is the Paul and Joan Quinault Distinguished Professor of Engineering and Adjunct Professor of Biology there at Dartmouth, and the focus area leader for biomass deconstruction and conversion at the U.S. Department of Energy Bioenergy Science Center, which is, I think, at Oak Ridge. He's the Executive Committee Chairman of the Global Sustainable Bioenergy Project. These are some of the other things you do. And the co-founder and director of Mascoma and Enchi Corporations. And I'll stop there and not take all your time to introduce you. And thanks a lot for being here. And over to you, Lee.
Thank you, Lou. Haven't done anything yet. It's very nice to be here. Very nice to be here. I'm really delighted. I've known of the Institute for Transportation Studies for a long time and never actually set foot here. Let's see, a couple of things. Lou mentioned all of these organizations I'm associated with. I'm reminded of John Prausnitz, who's a retired engineer from Berkeley, not so far from here, had a statement that's made quite an influence on me, which is that if engineering is the application of science for human benefit, then the engineer needs to be a student of not only the application of science, but of human benefit as well. And I would say that with the exception of the Global Sustainable Bioenergy Project, these other three organizations I'm part of are all along the lines of science for human benefit. But the Global Sustainable Bioenergy Initiative and this talk are focused on the issue of the human benefit piece. And so I can comment knowledgeably, I think, on a lot of issues related to entrepreneurship and innovation and technology. But with apologies if any of you came here to hear that, that's not what I'm going to be talking about. Essentially, the outline is my title, Need, Land, Carbon, and Development. It occurred to me that I maybe should say what I mean by bioenergy. There are, of course, a lot of specific issues that have to do with a specific value chain from a given raw material to a given end product. But there's also a lot of common issues that are related to using any form of biomass. So I'm going to try to put, with understanding that there's some risk and loss of specificity when you generalize, I'm going to try to talk about those common issues. So basically I'm talking about fuel, electricity, and heat from plant biomass. And there's a spectrum of things we can do now to things we hope we can do in the future. And that's one of the many reasons that people take different takes on this. And so you can have a sort of a low beam perspective or a high beam perspective. And, you know, it's a very responsible and needed thing to say, you know, I'm going to try to devote my energy to making sure we don't make mistakes and act responsibly. And I'd like to think I do some of that, but I will acknowledge unabashedly that my main focus is trying to think about how this might work. I think we need to, this meaning both bioenergy and the broader sustainable resource transition. I think in both cases it's going to take intent. It won't happen by itself. Let me just also mention by way of introduction that I find a pretty interesting question to think about a few hundred years from now. When people look back on the time that we're alive, what are the issues and topics that they're going to think we should have paid more attention, we should have been now paying more attention to? And in my opinion, the two that really stand out, one of them is what I call the sustainable resource revolution. That's an intentionally broad term, but I think of it as the transition of living from on our resource capital to our resource income. So you can apply that to energy. You can also apply that to water. I think it's going to be pretty obvious in the broad sweep of history that that was the big thing that in our lifetime, in the material sense, we needed to look at. But the second one is poverty. I could perhaps bore you with global poverty statistics, which I've become much more familiar with in the last few years. But I think that's also a profound issue, and also one that the world clearly has the means to do something about. I think we'll be held morally responsible on both of those. And by the way, I didn't mean to be preaching, but I'm reminded of a phrase I ran across from the great conservationist Aldo Leopold about a year ago, although he didn't write it a year ago. He passed away a while ago. But he said that ethical behavior is doing the right thing even when the wrong thing is legal and no one's watching. But in any case, so this is just a little comment about something, it may even be distracting, but something I know a lot about before we get to, and is part of this story, before we get to the need and the land and the carbon and the development. There was a lot of discussion with the group I went to at lunch about innovation and policy, specifically in the bioenergy and indeed biofuels domain. And just to have one slide on that, it's interesting to note that cellulosic feedstocks, one form of biomass, on a dollars per gigajoule basis for what you have to pay to purchase this stuff is very, very competitive, even with oil today. So if you start at something like $60 to $80 a tri-ton, take 80, go up over there, you get to about $27 per barrel of oil. So buying the energy as biomass, purchasing the energy as biomass, in an economic sense, is not the rub. But in the specific case of fuels, and again, I mean in general to be general, the biological, or for that matter, non-biological conversion of cellulosic feedstocks to liquid fuels is not cost effective. And in the case of, this is one place, I believe that the Department of Energy, who has a lot to do with what happens and doesn't happen in the United States, is botching things tremendously in the biofuel space. Not a little, but a lot. Maybe I'll just leave that for now, because it's not the main thing I want to talk about. So let's talk a little bit about the need that at least I and some others see. I'm going to focus largely, but not exclusively, on an analysis that Lou and I recently, in fact, Lou led. But to frame that a little bit, I think the two largest, in my view, the two largest energy supply challenges in getting to a low-carbon world I refer to it as the second half of the low-carbon electricity supply problem and the second half of the low-carbon transport problem. The bit about the second half goes like this. In roughly the first half of the low-carbon electricity supply, you can have backup capacity and still have a good amount of income to pay for that capacity, for its capital cost. But as you get to 70, 80, 90% penetration and you're barely using the backup, if you still need as much backup, then the economics of that are really, really difficult. There are solutions to it. It's not a dead end, but it's going to take fairly radical reform. In the case of the second half of the low-carbon transport, in a nutshell, it is my view and the conclusion of our paper that we have vastly more options for the first half of the low-carbon transport problem than the second half. And so this is actually more general than transport. This is referring to all bioenergy. And in blue, there's 5 different low-carbon energy scenarios here. The 2-degree scenario of the IEA, the Global Energy Assessment, IPCC, Ecofis, World Wildlife, and Greenpeace. So the blue for 2050 is the fraction of primary energy from biomass, and it varies from about 17 up to about 40 with an average at 25%. The green is the absolute amount of energy that entails. They're not proportional because different ones of these have different total amounts of energy, but it averages about 140 exajoules. And I just mentioned here, I won't read it all to you, but the highest one here, still takes what in general most of these studies take, and I think indeed should take, which is an other renewables first strategy. In other words, if you can do it by something other than bioenergy, we perhaps should, because we only have so much land and a lot of other things to do with it. And so from the paper with Lou, here's 7 different transport sectors and dates from 2010 to 2075. I want to focus here. If we look at the fraction from hydrogen and electricity, 80% of personal light-duty vehicles from either hydrogen or electricity. The big 3 in most people's thinking, if you want low-carbon transport energy storage, are hydrogen, electricity, or biofuels. And we also took, by the way, an other renewables first in this particular paper. We said, how far can you get without biofuels? And our answer was on the order of, by 2075, by the way, 70% of bus, 100% of rail, and 50% of road freight. My guess is that many people who would be excited about hydrogen and electric vehicles would rightly recognize those are large contributions. By the way, one thing I learned, I think Lou's known this for a long time, I was totally unaware before we worked together that ocean shipping is a larger use of energy today than aviation and expected to stay that way. In any case.
Although there's some new aviation.
I see. Okay. Well, I'll stay tuned. So if you roll that out to 2075, I'd really love to have a version of this figure, but that's green, by the way, Lou. I keep pointing to this Brand-Aid brown thing. But in any case, this pink thing here is the contribution of bioenergy. Very roughly 40% of the total, and actually somewhat larger than either the electricity or hydrogen. And so there's something like half, and by the way, the remainder that's not bioenergy is still, or biofuels, is still liquid hydrocarbons. So roughly there's half of a conservation-intensive energy future, and there are other energy futures. Notice total energy is flat here. Roughly half of a conservation energy future that it's going to be substantially more difficult to provide this without liquid hydrocarbons. Or to put it differently, it's substantially more probable we will use liquid hydrocarbons for about half of future transportation. It's also worth noting that this is the total allowable carbon emissions, about 25 gigatons of CO2 in 2075, compatible with a 2-degree scenario. And if, for example, we said, this is just too hard, this part of transportation that that we'll likely need liquid fuels for, it's just too hard to get that from biomass. Let's do it from fossil. And by the way, about all the efficiency that you can wring out of this has been wrung out. Then just from that amount of emission, you would have about twice the entire economy-wide allowable emissions for a 2-degree scenario. And one thing that struck me about this is I think, and this may be slightly oversimplified, and there are people in this room who know more about this, including our visitors from Warwick, I believe, but it seems to me a pretty good approximation or generalization is that the greater the distance between refueling, the greater the value of a liquid fuel. So I want to talk a bit about land, because if we're going to be led into needing biofuels, we better think about this. Small print, I apologize. This is, though, and again, I've been in this field a long time, and I only started to pay attention to these numbers about 5 years ago. So today, there's 1.5 billion hectares of cropland. Depending on how you count it, there's about twice that of pasture land. On the order of 4 billion hectares of forest, which is much easier to do with remote sensing, to figure out what's forest and what's pasture versus what's crop. Planted forests are vastly smaller, and urban and built-up land is smaller than that. If you look at trends over the last 10 years, we are actually using less land to feed people than we were in 2010. But if you break that down, we're using somewhat more cropland with larger losses in pasture land. Pasture land figures quite prominently in our story. There are only 3 quantities of land that can grow terrestrial biomass that in any way that matter. Algae is another matter. Let me put that aside. We can discuss it if you like. But I'm talking about terrestrial plants now. So, as normally categorized, it's cropland, forest, and pasture. I think pasture as a land category has particular potential for bioenergy. There's a lot of evidence, although as I'll discuss, the data is really remarkably poor on global pasture, most of it anyway. But there's a lot of evidence it's much less fully utilized than cropland and has much, therefore, greater sustainable intensification potential. But something I don't think that has been focused on much is that actually pasture is a minor contributor to global food production. Let me put a few caveats before I expand on that. So, global food production contribution is not the only important thing. There are ecosystem services, there are livelihoods that are supported on pasture, and some local circumstances have very different than the global average. Acknowledging all of that, it is still relevant to think about, so what fraction of dietary calories or what fraction of dietary protein actually comes from land that we classify as pasture? I'm going to give you just a moment to think about that, and if anybody wants to raise their hand and hazard a guess, please go ahead. The question is, what is the fraction of let's take dietary protein. I'll ask you one question rather than 2. What is the fraction of dietary protein that comes from pasture land?
There's twice as much pasture land as cropland.
Percent. What fraction of what we eat? Okay, it's about 3. Not bad. So if you look at meat, milk, eggs, and you look at the fraction of total protein globally, together they're 30% of total protein, all of those together. Keep in mind, let's just focus on the meat one for a minute. Globally, we use more poultry than beef or pork. We use as much pork as we use beef. And poultry and pork essentially don't require any pasture land. And most of beef globally is actually not supported on pasture land. Much of beef is supported on so-called mixed land, which has both animals on it and crops are grown in the same year. So that's excluded from pasture in this particular scheme, the way the FAO does it. But look, if you multiply the fraction of total protein in the diet by the fraction from pasture, you add them up and you get 3%, and you can consider, for example, the fraction of land that the animals that are grown in feedlots spend on pasture, and it doesn't change the answer. By the way, for calories, it's about 1.3%. So I said the caveats first about all the reasons this land base is important other than global food production. But for global food production, this amount of land that's 2 times as large as cropland is not a big contributor. So the curve here is actually not what the data looks like, but what I want to do is to get you used to this plot, all right, so that you can interpret it. I'll show a few figures that are. So here we have, imagine the world's agricultural land, both pasture and cropland. And when I say pasture in this context, I'm including rangeland, although range and pasture can be differentiated. But take the whole kit and caboodle, about 5 billion hectares of the two combined, and imagine rank ordering them from the acre that has, or the pixel or what have you, that has the lowest contribution to food supply up to the highest. So the thing needs to be concave upward. And so for a given value on the x-axis, the value that's plotted is the percentage of food from all land less than that. So if you have lowercase a, and it comes over to 40%, then this amount of land produces 40%, and this amount of land produces 60%. Okay? So the data has not yet at least been compiled to exactly sketch that curve, but I'm pretty sure we actually have enough information to know what it looks like. It looks like this. So here's your, and I should have fixed this. This scale should go out to 5 billion, but the qualitative thing is good enough, I suppose. So here we are at global pasture land and 3% of protein. Here we are, a 2014 paper in Science from the John Foley Group in Minnesota said 86% of food and feed production is produced on 58% of cropland. 58% of cropland is a little less than 1 billion acres. It's 900 or so million. So basically, we feed the world on about 1 billion hectares, and we use about 5 billion hectares, whatever quality, of land that we classify as devoted to food production. And so it's interesting to compare that to the amount of additional cropland we could have, which is a hard thing to estimate and somewhat controversial and has all sorts of consequences. But the FAO has estimated how much land we have with rain-fed crop potential. Not all of those consequences are bad, by the way, but there are a lot of consequences. They estimate that we have 1.4 billion hectares of prime and good agricultural land globally that is not now cropland but could be, and another 1.5 billion hectares of marginal or very marginal land. How does that compare to what the FAO projects we will need by way of new cropland to feed the world? And the answer is 70 million hectares, or about 5% of this. So part of my message to you, and there are knowledgeable people who would disagree, I think, I'm pretty sure, but part of my opinion, my assessment of this field, is that there are many challenges to doing this right, but geographic potential is not particularly one of them. In other words, there's plenty of places you can grow stuff in the world, but there are many other barriers that need to be thoughtfully negotiated. This is somebody else's view. I had absolutely nothing to do with this. Although I think it is fair to say that this is a bullish view, a favorable view, perhaps a looking for answers view, although different people would categorize it differently. This is by Ecofis and the World Wildlife Fund. And so they go, look, you start off with 13.2 billion hectares. You exclude all protected land, barren land, urban areas, and water bodies. That takes that gray away. And then you exclude all current agricultural cropland, all unprotected forest land, all land not suitable for rain-fed agriculture, and you get to G, 893 million hectares that has potential for rain-fed agriculture beyond current cropland, current forests. Now, you might argue we'll need more cropland, and I just showed you at least the FAO's opinion of that. This is the World Wildlife Fund, and they say, well, you know, we're going to take another 220 million hectares for increased protection of biodiversity. That brings you down to 673 million hectares. By their estimate, if you took 40% of that, 250 million hectares, and devoted it to bioenergy, you could produce 40% of primary energy. And it's interesting also where that land is and what type that land is. So the assessed potential is located on grassland and non-densely vegetated woodland. Most land of these types is currently used as low-intensity grazing lands for livestock. Although this is 3 years old, it is, to my knowledge, the FAO's latest, they don't do this every year, it's the FAO's latest sort of comprehensive look towards the future. I was truly surprised, frankly, by some of the statements in this, and I'll just share some of them with you. This was not what I thought would be a mainstream view of feeding the world. First, growth of world food production needed to meet the growth of demand will be lower, they're talking about the future, than in the past, even after accounting for increases in per capita consumption and changes in diet. Number two, based on our assessment of world agricultural resources, it seems that at the global level, there should be no major constraints to increasing agricultural produce by the amounts required to satisfy the additional demand generated by population and income growth to 2050. The forces that shaped the rapid growth of meat demand in the past are expected to weaken considerably in the future. And for the world as a whole, the pressures on agriculture to produce more food for the growing population will increase beyond 2050 by much less than the indicated in our projections of the period to 2050. So if you put the first and the last statement together, what at least this report of the FAO implies is that the period from now till 2050 is going to be somewhat less challenging, at least in terms of growth of production, than the period we have just been through, and the period after that, yet less challenging still. This is a little hard to see from the back row, but we've got 5 different categories in the developing world and 1 lumped category for the developed world. The dark blue is agricultural potential cropland that is expected not to be used by 2050. The light blue is currently used cropland, and then this little crosshatched bit is the projected additional cropland. So the world will be adding cropland, according to this, in 2 places, sub-Saharan Africa and Latin America. The developed world will actually use less land to feed itself in 2050 than it does now. And sub-Saharan and Latin America, of the share of the usable balance of land is 84%, and indeed, half of the global total of projected unutilized cropland is in only 7 countries. And so this is not something that's evenly distributed. Those are, by the way, Brazil, Argentina, Sudan, China, Democratic Republic of Congo, Angola, and Mozambique. So at the global level, there is lots of land beyond what's needed for food. Now, in other words, there's lots of land that could grow food that is not expected to be needed to grow food. That available might not have been the best choice of words. I think I actually just said it better. But there are a lot of other things to think about, even if that's not a particular challenge. We have to make sure that any land use changes are graceful and that sensitive lands are spared. From a social point of view, we have to ensure that the benefits of bioenergy are distributed, and especially that they don't make the poor poorer. And from a food security point of view, this is the same report that talked about there being so much capacity. But it says food security is only weakly linked to the capacity of the world as a whole to produce food, to the point of becoming nearly irrelevant. So just because the world is not going to run out of the ability to feed people is by no means any assurance that people won't be hungry. In fact, we have plenty of capacity to feed the world now, and then there are significant problems with food security. So I mentioned pasture, and I have given entire seminars on the subject of this slide. It's the largest land category managed by humans by a factor of 2. It is, everybody thinks, the most important land category for expansion of food crops to the extent we need to do that. It is, at least in my opinion, the most important land category for expansion of bioenergy. It is home to most of the world's poor, who are rural poor, not urban poor, 2/3. There's incredibly scant data of very poor quality. It's really hard to know what's going on this land. We have a much, much better idea what's going on in cropland. And there is very likely large intensification potential, i.e., we could get more output from this land. Let me just give you a little flavor for the analysis we're doing. John Sheehan is leading this along with Mario Herrero. I'm quite involved as well. Mario Herrero is probably the leading global pasture expert. But it's an interesting approach, and it's actually adapted from what John Foley and his colleagues at the University of Minnesota did for crops. They said, let's bin the world's, I will talk about, we're doing it on pasture land. Let's bin the world's pasture land into 100 equal geographical area pieces. based on the precipitation and the degree days, or if you will, temperature. In other words, based on climatic variables. So if you normalize for climatic variables, there's some subtlety to it, but the main thing left is management or local demand. So for each of the 100 bins, as we call them, you can look at the distribution of the actual yields that are achieved on that pasture land, and you can ask questions like, what if we brought the whole world at least up to the current 50th percentile? How much more agriculture, how much more livestock could we produce? What if we brought the whole world to the 75th percentile of the climatically constrained potential? And you get this sort of thing. These plots are actually very informative because the area under the curve is current production, and the area over the curve is potential production that we don't realize. And if you look at the same thing for crops, they fill much more. They fill much more of the diagram than pasture land does. So how many of you here have heard of either the or a global calculator? How many people have run into that? Some, a few? I would really suggest, if you're at all interested in climate, that you just Google global calculator. You will very quickly find this. It's a little hard to see, maybe, but it is quite a remarkable exercise. And in fact, one of the reasons it was developed was to serve as a tool for governments and policymakers and negotiators at the upcoming Paris meeting. There were something like 20 national calculators as well as the one that is called a global calculator. And countries are customized. They didn't all start with the global ones. Some of the national ones happened first. But countries are customizing these for their own purpose. China has a very well-developed national calculator. But basically what's going on here is you've got some lifestyle choices, some technology and fuel choices, some demographics, and some land and food choices. And the way they structure it, and you could talk a long time, and they did talk a long time. This was really quite an impressive effort, done over a remarkably short period of time. I think it's really impressive. But every one of these, there's actually subcategories with each one. The number of subcategories is the bars. So like there's 4 subcategories here, there's 5 subcategories there, in all well over 50 variables. And you can go in and you can set every single one of them from level 1 to level 4. And I'll define those in a moment. But essentially from very little effort to very large effort, they will talk about the global GDP impact, they will project the climate impact, and a variety of other impacts. This is not the only window. It's quite impressive. And so what I want to focus on is variables in the category of diet, variables in the category of renewables, and variables in the category of land use. And it's pretty interesting. So 1 is minimal abatement. These are their words. 2 is ambitious. 3 is very ambitious. 4 is extremely ambitious. As Jeremy Woods explained it to me, who was involved in this, very ambitious means most experts think it's possible. That doesn't mean likely. And extremely ambitious means actually a minority of experts would say that it's possible. So you can imagine the discussions that would go into such things. But look, here's all renewable energy from number 1 to number 4, plotted in terms of percent change, in terms of greenhouse gas emissions over here, and also in terms of the global temperature. This is relative to the IEA 4-degree scenario, which to the year 2100, which according to their assumptions actually resulted in 3.2 degrees, although it's called the 4-degree. It was calculated somewhat differently. But the striking thing, it's easy to think about climate change mitigation as being a matter of energy supply and utilization. And that's the way a lot of people talk about it. I don't think we need to get stuck on which exactly one of these is more important, but clearly, diet and land use have a roughly comparable and conceivably even larger impact than everything we do in the renewable energy sector. By the way, independent of bioenergy, one of the greatest risks I see to near-term global and other climate policy is that we will leave agriculture out. We will leave land out and focus strictly on energy supply. Well, when you've got these kinds of 500-pound gorillas running around, I think that that's not a good idea. And so smart smart land use decisions are an essential part of any desirable climate scenario, with or without bioenergy. All right? With or without bioenergy. Finding room for about 140 exajoules, and that was the average of that 25% supply of sustainable bioenergy, is likely doable, assuming intent. I don't think the entire sustainability conundrum, I don't think we're going to solve by accident. I think we're going to have to do it with intent. And I think some would say this is not even our biggest land use challenge. The thing I would like you to think about, though, is the risks of action in the bioenergy domain compared to the risks of inaction. And in fact, Lou and I had what for me was a somewhat new conversation just as we led up to this, which is that there was a period of really high excitement and anticipation for bioenergy, somewhere in the 05 to 07 range. You could argue plausibly that there was a period of time that the risks of action were greater than the risks of inaction. My personal view is that today the risks of inaction are substantially greater. Different reasonable people would disagree on that. Let me talk to you a little bit about carbon, which is part of this story. So in 1991, a group of people and I published a paper in Science. This was specifically about ethanol, but it's actually, the principle is true of any bioenergy, and that is you have the potential, which doesn't mean you'll realize that potential, but since CO2 removes carbon from the atmosphere, and then whether you burn that in a processing facility, an electrical generating plant, or in a vehicle, you return one and the same carbon to the system. And so as long as you don't muck things up, you have the potential for carbon moving in a circle. Mark DeLucci, by the way, who was until recently here at ITS, was one of the very first people to point that out in 1989, actually, in his PhD thesis, which was from you sure? I thought it was postdoc at Princeton.
Oh, his postdoc was Princeton. Was it here?
I think it was here.
Here. What am I saying?
I think
it's here.
I think it was here. But this story it is recognized to be more complicated than that circle would imply. So Tim Searchinger was not the first to point out this concept of indirect land use change, often abbreviated ILUC. But I think it is fair to say that his paper and ongoing analysis has been one of the most influential in bringing attention to this issue. So he published a paper, and others, published a paper in Science in 2008. And the basic idea was, if you've got land that's producing food now, or anything else, I suppose, and you come in and you replace that land use with bioenergy, but you're still going to produce that somewhere, then somewhere else is going to have some land use changes, which could be anywhere from very benign to draining peat bogs or something, which has tremendous carbon releases. And we need to think about that. Julie here is an expert on this. She knows more about it than I do. But for various reasons we were talking about at lunch, this was Searchinger's estimate in terms of the grams of CO2 emissions that you would add to the physical emissions for the indirect effects. And there is a progression as you go in time towards it getting smaller. There is a view, which as far as I know is relevant at least, it may not be the end of the story, that when it was this big, you could take a pathway that would otherwise be very meritorious from a carbon point of view, and it would go from being a lot better than the status quo to being worse. It was a sign changer. From a mathematical point of view, if it's this big, that's no longer true, although I don't want to oversimplify the matter. Then there was something called the Manomet study from the neighboring state to mine in Massachusetts, because people were talking about harvesting forest biomass to produce electricity with the notion that when they did that, we would save greenhouse gas emissions because, after all, that CO2 was removed to grow the trees, and therefore we would just be returning it in a sustainable cycle. But the Manomet people looked at it and they thought, actually, most forests in New England, and this is correct, are removing carbon now. If you leave them alone, you will remove carbon. And so you need to compare the carbon you will save by displacing fossil fuel-generated electricity with the carbon you would save by leaving the forest alone. The do-nothing alternative was not zero. And in fact, it turns out that if you're only making energy products, whether it's fuel or electricity, and you clear a forest in year one, and you clear an acre of forest, you convert it all to energy, and you displace fossil fuels with the energy, and at the end of that year, you will have higher emissions than you did if you would have done nothing. That is a fact. That is a fact. And so they talked about this concept of the carbon debt, after which the system has to play catch-up. And I am not here to stand before you and try to debunk every carbon criticism of bioenergy. I think they're basically right. Okay? That doesn't mean all bioenergy doesn't make sense, but the specific case of forests is more problematic in my view. Back to Tim Searchinger, his latest. He and also John DeCicco talk about, remember John?
John's been here, I guess he hasn't presented.
Yeah. The most important part of this, and these claims are out there, that, you know, if you're going to compare bioenergy to growing plants anyway, simply diverting them to bioenergy does not remove any additional carbon from the atmosphere compared to what would have happened. Now, that's Searchinger's view. He's not the only one. This issue is quite contentious. I think this statement is conditionally true, but as a generalization, it's wrong. Or at least there are important exceptions to it. I'm going to present an in-process analysis. The ball is still bouncing, but I think the trends will very much hold up. And the bottom line is, I think there are circumstances where it's radically better, from a climate point of view, to leave the land alone. There are circumstances where it's about equal, from the climate point of view, which is only one point of view, to leave the land not in management versus to manage it for bioenergy. And I think there are circumstances where it's radically, indeed on the order of 100-fold, better from a climate point of view to produce bioenergy than to leave it alone. Now, that's not today the consensus view, but frankly, there is no consensus view today. It's a very confused field. So we think there's three important variables. One is, what land cover do you start with? Pasture, forest, or cropland. Two is the production technology, but it turns out actually that the production of the energy crops makes more difference for this analysis than the maturity of the actual conversion. And then three, which is one that's been largely neglected, is, well, if it did go to an unmanaged state, what would it go to? Would it go to a forest, or would it go to a grassland? And so I'm not saying no one's done any work, but I don't think anyone's framed it quite this way. So let me just focus on the results. If you start with forest and you produce biofuel, from a carbon point of view, you would do better off to leave the forest alone under most circumstances. There's some tricky things. So over here, this is the unmanaged state. This is the biofuel state. Electricity is similar, by the way, directionally the same. So you would do better to leave it alone. On the other hand, if you start with pasture or cropland, and you talk about current production technology for bioenergy, within the margin of error of such analysis, it's the same. If you talk about future biotechnology, future production technology, you can, I think, reasonably imagine getting larger carbon benefits per acre compared to land that starts off as cropland or pasture, but would revert to forest. In other words, if you left it alone unmanaged, it would go to forest. But if you start with land that would revert to grassland, and recall that in that study projecting 40% of global energy, they were talking mostly about low carbon inventory lands, then you would get radically larger gains from going with bioenergy. Okay. Let me talk a bit about the people side of this, the development side. So we've got a very complicated system here involving food, land management, development, environment, technology, without bioenergy. It's a very complicated system. And if you add bioenergy impacts every one of those. And without a lot of analysis, I think that picture is enough to say, gosh, if we did this badly, we could muck a lot of things up. And if we did it if we did it well, we might be able to make a lot of things better other than only energy supply. Again, acting with intent. So I recently had the privilege of working with a bunch of authors from Africa and Brazil, a paper called Bioenergy and African Transformation, and we wrote, bioenergy production requires land and is thus inextricably linked with social development, agriculture, and environmental quality. These linkages increase the complexity of analysis and deployment of bioenergy and can result in undesirable consequences if managed poorly. If managed well, they have the potential to greatly multiply the benefits beyond energy provision per se. I will venture to predict that bioenergy development in the past has been more motivated by things other than energy supply, both in Europe and the United States, mostly motivated by rural economic development. And I think it will continue to be the case that factors other than energy supply will play a major role in this. Jeremy Woods and I wrote in 2011, this is specifically with respect to Africa, consideration of the impact of bioenergy on African food security has tended to focus on land competition and to overlook bioenergy's marked potential to promote rural economic development. However, potentially productive land is rather plentiful in much of Africa, whereas lack of development is the most important underlying cause of hunger, with energy poverty also a significant contributor. And if you look at land available per capita and you divide it by energy demand per capita, Africa stands out as having really plentiful land resources. And even when you consider quality, August Temu from the World Agroforestry Center wrote, I heard him say this, I found it remarkable. Africa has about 12 times the land area of India, similar land quality, and 30% fewer people, yet India produces enough food to feed itself and Africa does not. The Green Revolution bypassed Africa primarily due to serious organizational and institutional weaknesses, not geographically limited capacity. And so, again, as I try to sort of think about, if engineering is the application of science for human benefit, what about the human benefit piece? I've been paying a lot more attention lately to food security and insecurity. I've become familiar with the way the FAO talks about this as of about the last dozen years. They talk about food availability, food access, food utilization, and food stability. I just can't get over that those seem to me, I know what one of those means. I know what stability means. The other ones I, for one, find kind of opaque, but I particularly find them opaque in terms of relating them to the impacts that bioenergy might have, positively or negatively. I think a much better framework from the point of view of thinking about food security in relation to bioenergy is thinking about the causes of food insecurity. These are the ways you measure. These are categories for measuring. Measuring does not imply cause. And so every once in a while I get really excited about a book and I send it to lots of people. But the first one of those was a book called Enough, Why the World's Poor Starve in an Age of Plenty, written by Roger Thoreau and Scott Kilman. Roger Thoreau has an interesting story. He's about my age. He'd worked for 30 years as a Wall Street Journal reporter and was assigned to cover the famines in Ethiopia. And he got so outraged that he quit his Wall Street Journal job, and he's a 100% food security guy now. And they talk in their book about why it is that people are hungry. First and foremost is poverty, far and above, but also poorly developed infrastructure. And one of the things that they develop is we're not talking only about physical infrastructure and knowledge infrastructure. Market infrastructure is really, really important, and I'll give you an example of that. Food aid has been administered generally by both the EU and the United States. It's getting a little better, but it's been generally administered for the benefit of the producers, which I think is immoral, rather than the recipients. Poverty and food security really should be viewed as more one problem than two, and I'll tell you a very easy way to see that. How many hungry rich people do you know? I rest my case. So what's interesting is if you look at the actual causes of food security, for most of them it is really not a stretch to imagine, at least if you get out of the mindset that the world is absolutely limited in agricultural land, which I think is not true, And you start thinking about these, boy, local production being undermined by foreign subsidies. Well, if you're producing food locally, that really helps that. Incomes, rural economic development. I want to focus, though, on the potentially most problematic one, which is bioenergy from food crops and the impact on food prices. And I put that as sort of either or, and let me tell you why. So I know several people that are working on the hypothesis, and by the way, I haven't spent most of my life working on grain-based biofuels or bioenergy, but I think this is interesting to contemplate. Folks are working on the hypothesis that in a situation where you're not limited by land, and you in fact can grow more stuff, that producing biofuels, specifically from grains, would stabilize food prices. And the way that Thoreau and Kilman described the famine in Ethiopia, Ethiopia actually, it turns out, geographically speaking, is a pretty good place to grow grain. Norman Borlaug spent some time there, as also described in that book, trying to help Africa come along. And they had a great year in 2003. Lots and lots of grain, making progress. What they did not have was functional markets. And so they had nothing to do with overproduction. Prices fell through the floor. And the following year, the farmers said, well, that took a beating on that. I'm not going to plant so much of that the next year. And they had a drought. And that led to the largest famine in the last 15 years. And so they had better than usual year preceding a bad year, basically. And I don't want to go through, we need to get to discussion here. I don't want to go through all of the details, but the hypothesis, and it's only a hypothesis, the hypothesis is that had they had bioenergy to stabilize that, or in general, that there's a price stabilizing potential. And interestingly, I think it is a rather widespread view that corn prices in the United States would have been higher in the drought of 2012 had there not been biofuels. What actually happened was the biofuel plants shut down for the summer, not because they're good guys, but because the feedstock was too expensive to compete into fuel markets, and therefore there was more corn on the market than there would have been otherwise. My point in this particular part of the discussion is not issue solved, that's the only way to look at it, but rather the notion that even from a food crop, that bioenergy necessarily has a bad impact on food security and availability is a longer discussion. But let's go back to the idea of agricultural development. So Wilson Conway in Can We Feed the World said agriculture typically counts for 80% of the workforce and 50% of the GDP in developing countries. There's nothing else that's as important. A 1% gain in GDP originating from agriculture generates a 6% increase in overall expenditure of the poorest 10% of the population, whereas a 1% gain in GDP originating from non-agricultural sectors creates zero growth in overall expenditure of the poorest 10% of the population. There's a substantial literature which suggests disproportionately large benefits to the rural poor from agricultural development as opposed to other kinds of development. And indeed, and this is one case where I think we're starting to come around. In the 1990s, there was a widespread notion that among aid organizations that hungry countries feeding themselves was not very hopeful, but they needed jobs in manufacturing and underwear and things of this kind, manufacturing that would give people money and then we would just import the food from elsewhere. Fortunately, we seem to have moved beyond that. Brazil is not perfect, but it is the foremost example of bioenergy deployed in a developing country context. It is also a fact that social development, agricultural development, food security, and bioenergy development all happen together. Now, that doesn't mean one caused the other, and it's a very difficult intellectual exercise to say, well, what would have happened had bioenergy not been part of that mix? All we can say is that bioenergy didn't prevent it from happening. Yeah, sorry, I'll wrap this up. The person who in the world who I think knows more about, who's actually measured more social impacts of bioenergy than anyone else I know in a developing country context, is Marcia Azenia, and these are slides from her. Sugarcane in Brazil is used for both ethanol and sugar, and so it's the largest employer in the agriculture sector in Brazil. It's the largest fraction of workers in the formal economy who have have insurance and unemployment and things of that kind. If you look at the tax revenues of communities to which ethanol plants have come in the last 15 years, they go up dramatically. If you look at the level of education community-wide, it improves. These are from our paper. I find these quite remarkable. Brazil produces 9.3 gigawatts of electrical generating capacity now from bagasse. Brazil has about 40%. It used to be 50%. 40% of total energy supply in Brazil is low carbon. Hydro is the biggest. Bagasse is the second biggest. Sorry, bagasse is the solid residue left over from squeezing the juice out of sugarcane for ethanol or for sugar. That's equal to 1/3 of the 28 gigawatt capacity of the 47 sub-Saharan African countries other than South Africa. It's also the case that under current conditions, the production of bioethanol per unit of energy produced, compared with essentially coal, hydroelectricity, and oil, requires 38, 50, and 152 times more human labor. Now, interestingly, the source of that is Jose Goldenberg, who's quite a distinguished individual. And I asked him, I said, well, Jose, did you look at other renewables? And I was surprised by the answer, because he said, yeah, actually, solar is a little better than biofuels, and wind is a lot worse. But the point is, if you're talking about the social benefits of different kinds of energy and the employment possibility, they're not created equal. So Lou reminds me that I need to wrap it up. I have a few more slides, but let me just tell you what they're about, and maybe just put this up as something to think about. So if you look at local human well-being, and you imagine the blue as a baseline, green would be terrific. Bringing the poorest people up the most would be even more terrific. But a lot of people worry about this one, namely, the average may get better, but the poorest of the poor get even less. And so a network of people out there are trying to think really hard about this. Just a few observations. One, there's a certain tendency when thinking about bioenergy in a developing country context to assume that the only appropriate bioenergy would be small. And I think that's really interesting, because on the one hand, it's almost like duh, and it certainly it solves the problem that if small operationally means that the capital can come from within the community, then obviously the community, whatever that is, will have a lot more control than if the capital comes from the outside. And we've all seen the colonial movie and have no need to see it again. On the other hand, the idea that only simple small technology is something that ought to benefit the developing world can also be seen as very paternal. And so it's tricky. There are larger challenges, there are distinctive challenges, actually, to making both small bioenergy and large bioenergy work in a developing country context. On the small side, the challenge is that to make these things viable technically and financially is probably more difficult, often small than large. On the large side, it's this business of having external owners and not getting into an exploitive situation. And directionally, without getting into what we could spend more slides on, I think you'll probably believe that at this point, directionally, the model we think is really interesting is to think about a relationship between the corporate producers and NGOs rather like the ones that has been really actively promulgated in the environmental field over the last 10 or 15 years. So, for example, the NRDC has relationships with Walmart and with Home Depot. And interestingly, when I was in my role as a cellulosic ethanol founder of a company, we were approached by the NRDC. And they said, look, you want to be seen as green. People will believe we're green. They're not going to believe that you're green. And if you let us have an impact on how you do business, we will stand with you. This model happens in the environmental field. We think it's a really interesting model in the social field, where there's, in essence, a stakeholder for social development. Why don't I stop? Thank you very much.
Thank you, Lee. I suspect there might be one or two questions. All right, Jacques, why don't you kick us off? Jacques Franco, you might know him.
Hi, Jacques.
Guys have never met. Bioenergy guy.
Manomet study.
Yes. For the record, I gave a short answer. They do. I'm sure they do. Yes. Okay, and I'm reminded, if I forget any of those questions, come back to them. But I'm reminded that this is being recorded and I'm supposed to repeat things so that folks who aren't here can understand. So backing up, I was asked a question, does the Manomet study consider displaced fossil emissions? The answer is yes. The comment, which I don't want to miss, is that the primary cause of poverty, I believe you said, say it again, is cultural violence? Is cultural violence. That was the comment. And the question was, what about bioenergy in relation to water, waste, and nitrogen? And I will try to be brief. In my view, just as poverty and food insecurity are in many ways more one problem than two, I think in the context of bioenergy, at least, that water and land are more one problem than two. When I talked about there being plenty of land, that was plenty of land with plenty of water, or at least enough water for rain-fed agriculture. And so actually getting access to that land in viable ways is really tricky and has a lot of complexity. But if you do that, the water problem comes with that. It's not separate. It's integral. So I think there is enough land with enough water to feed the world and to do lots of bioenergy if we do it with intent. As far as waste, depending on how you produce the bioenergy, but you've generally got certainly a biological raw material, and you've often got biological conversion processes, and those don't tend to produce biologically offensive waste. I mean, you have to take care of oxygen demand and things of that kind, but there's no waste that anyone I've ever heard anticipates that we don't already know how to take care of. Whether we take care of it is a completely different matter. When it comes to nitrogen, there's a couple of issues, as everyone knows. There's nitrogen released to the environment, which can be a source of eutrophication. And there, again, we know how to prevent that. That doesn't mean we will. And indeed, if we go to grasses as energy crops, that's nature's nitrogen sponge. People talk about planting bioenergy crops beneficially along waterways in order to prevent nitrogen from cornfields and whatnot from going into the water. That doesn't mean we will do it. We can do it. As far as the nutrients to grow the biomass, again, I can point directionally to the solution, and I'm going to have to say again, that doesn't mean we'll fully implement. But directionally, if you put a box around a bioenergy facility and imagine some combination of organic fuels and electricity leaving, notice that there are elements coming in with the biomass, the elements you remove from the field, the nitrogen, phosphorus, potassium, and none of those are in the products you're selling if you're selling electricity and fuels. And so what you want to do is to recover those nutrients and put them back. There's a longer discussion, but that, in the spirit of looking for solutions, and we also need to avoid problems, that's the other side of the coin, I think that's the direction the solutions lie. Yeah? I will give you one answer from Brazilians. From Brazilians, many Brazilians have said to me, it never would have happened if we didn't have a dictatorship. That's part of the answer. It's also part of the answer that if you look at the primary productivity capacity per capita, Brazil is, for a country its size, singularly large. That didn't hurt either. One other comment about Brazil, where I've lived and I have lots of friends and I go often, and I think, by the way, is, well, one other comment about Brazil.
You have to say what? What is it, by the way?
I think for many bioenergy applications, it's the best place in the world to move them forward from sort of a commercial point of view. But it's an interesting comment in Brazil, and I've heard this from people who know very deeply and have been involved in all of this. They say, you know, we got into ethanol for purely sort of macroeconomic supply reasons. We were not trying to provide social benefits. And yet they believe they measurably did. And they say we got into biodiesel from soy with the goal of providing social benefits, and they consider it to be a failure. Now, I'm not saying, in fact, I hope it's not true that if you try to have social benefits, you will fail. But recognize that right now, the vast majority of bioenergy projects in the world, whether or not you get social benefits is an afterthought. They weren't designed with that in mind. And I think the same thing is true about environmental benefits, by the way. And I think we need to think about the government in many parts of the world that have a lot of bioenergy and a lot of social development needs are very weak. I think we need to think of governance structures that don't rely on strong government. And I think this notion of an NGO partnership may be helpful there. Yeah, we'll come back to you in just a sec.
About sort of the changes to the background system that might kind of complicate this analysis, both from the inventory of arable land direction and also this sort of carbon reduction pathway. So just thinking about affluence and climate change and this trajectory of the background system. So, when you talk about sustainable energy for all energy development, that's becoming a market opportunity, right? Private companies are getting into it because there's a new market for them. They perceive that these developing countries represent huge new market potential, and so they're getting into
Probably a good thing.
It's probably a good thing, but it's profit driven, so maybe it's not a social goal. But then on the other side, climate change is probably changing these trajectories for the amount of arable land. It's particularly going to have disproportionate regional effects. So I wonder, taking those two kind of things into account, how does that kind of confound this analysis a little bit as far as both the amount of arable land and also the potential for reduction? I mean, at 2 degrees seems like kind of
You're right that it's complicated. I think with respect to the first one, namely, so the private sector would see the opportunity and move in. I think there's a classical example of if we structure it so that societal values impact the decisions of the private sector, that it's potentially a very good thing that the private sector. I have more confidence of the private sector to properly constrained provide energy technology to the world's poor than I have in the world's governments. That's my personal view. So I think it's a reality we just about have to deal with. It's unavoidable, and I don't think it's necessarily a regrettable reality. It's probably the best way to make things happen, and yet, like everything, it can screw it up. Climate, my understanding, and again, I'm not a climate scientist, but I've tried to talk to people who are, and Lou, you certainly know a lot about this. My understanding is that what's absolutely clear about the impact of climate on arable land is that the best places to grow things are going to change. And some places that are okay to grow things now are going to get worse. Higher temperature, other things being equal, is going to lose us more growing capacity than it's going to gain us. Partly because of geometry, actually. There's more land that's going to get hotter than it's, anyway. But on the other hand, high CO2, other things being equal, is going to bring it up. And so the people I know are not quite sure how that's going to play out in global averages, but we know it's going to change locally. Yes, it confounds it. I think in my particular view, at least, if we don't do bioenergy, we are going to have a much harder time getting to a low-carbon world for reasons we talked about. And if we do use bioenergy, it's going to be complicated to get to a low-carbon world. And if you want to talk about the probability of getting a low-carbon world without it versus with it in complication, well, I think understand where I'm at, but that's really the question that's on the floor, okay, to try to be fair about it. And there was another... Yeah. Thank you. Let me see if I can repeat that. That'll really test if I was listening. Okay. So you commented that you thought that, I believe, the carbon benefits depend a lot on what you start with.
Yeah, we can argue whether the environmental benefit is good or bad for the environment.
Yeah. I think the most neglected one is what the land would revert to if you stopped managing it. I think that's also very important, but it's in the same.
But it's also
It's in the same family, and I'm trying to reflect your views, not mine here. Okay. So I think you also said that you thought there are cases where there are demonstrable energy benefits, and I think you mentioned Brazil as having demonstrable fossil fuel substitution benefits, and which are separate from the environmental scorecard, which is complex. Tell me if I'm getting it. And then you said that, but the social benefits, I believe you said in Brazil you feel to have been large, the social development benefits, right?
Yeah, I think in Brazil or in Africa,
Okay.
for example, you were talking about this also, it's probably going to have
And then you said, I think your closing comment, was that that's compared to a really small amount of current use, and if you have a really big current use, there may be a much smaller contribution. Yes,
ethanol from an energy point of view.
that's what they've told
About
me.
the other way.
Yeah.
Then the only real benefit I see in biofuels is the social.
Okay.
So,
Let me offer at least a perspective.
and then you said that when they had a policy oriented towards social,
If any of this were simple, we wouldn't be here. Let me just offer you, believe it or not, one analysis that's in process I didn't talk about. So we're actually quite far along on this, and what it's relevant to doesn't settle the issue, but it's relevant to, could we make a big difference in a country with really high demand? So we looked at the United States, and remember the gigantic impact of diet up here when I showed those bar graphs? So we did a thought exercise. We said, what if the United States were, instead of our current diet, we considered two alternative diets. One, half as much beef replaced by poultry. And lest you think that's totally crazy, beef consumption per capita has been declining for 30 years in the United States and globally. Beef consumption per capita. And the second diet, and I'll acknowledge Ethan Davis thought of this, I didn't. He said, what if we followed the USDA's health recommendations? All right?
Crazy idea.
And the result in round numbers is that you could provide the United States gasoline consumption from those kinds of dietary changes. That doesn't mean we will do that, but don't underestimate the importance of the demand side of the equation, especially in a country that has a lot of demand. It tends to be one of your biggest levers. Are you?
I could ask you anytime. But going back to your very interesting analysis of pasture land, and then you showed your categories where, depending on what land would revert to, and
Yes.
depending on what you try to grow, you could have anywhere from a increase in net CO2 to a pretty strong decrease.
I believe that to be the case.
The logical next step would be to now parse out the world's land, and maybe that was part of the bin analysis, I don't know, but to understand what would be the potential biofuel production in your best combination, or maybe you don't know enough about what land reverts to, I don't know.
Well,
But I'd love to know that potential. That looks like a big part of winter.
we have a project, I might have also mentioned, the Global Sustainable Bioenergy Initiative has a scholar exchange program which will pay for people to go to Brazil or Brazilians to go somewhere else to work on these kinds of things. We have a project that's starting which is aimed at exactly the kind of global mapping you're talking about, but in a qualitative sense, I can already tell you the answer. If you start with land that does not have a large carbon inventory, i.e. don't start with forests, and it would revert to land that wouldn't acquire a large carbon inventory, namely it would revert to grassland, and there's a tremendous amount of land in that category, and it's actually not even that hard to tell where it is. It's essentially the map of natural grasslands in the world. you will get much, much larger benefits from bioenergy than you would get from leaving the land alone. And I think the simplicity of that is actually powerful. We have yet to submit it. We'll see what the reviewers think, but anyway.
But does that get you to something like the bioenergy numbers that our paper?
Okay. I think it gets you to, compared to 50 exajoules, if I had to guess, I think it would get you to 400 or 500, that kind of analysis. So I think it's an order of magnitude larger, but that's a seat of the pants guess. I have not been through the analysis. And a critic would say, yeah, but if you've got to make it ecologically sound and socially sound, you have more than climatic constraints, and it's never going to be that big. And so I'll say it for the critics.
So I guess I'm curious more about the biofuel.
Yes.
Seems like it's only
Okay, so I need to try to repeat that question as well. So the question, and it's actually good practice because I can actually think about it as I do this. So I believe the question was, with respect to the potential social benefits of bioenergy, there would be rural employment, but it seems that people are increasing their standard of living by, in fact, moving out of rural areas to urban areas. And so to what extent is this swimming upstream or ineffective or something along those lines? Well, one could presume that it seems to me one could make an argument that what people are doing is moving from where there are no jobs to where there are jobs. And right now, that's from the rural communities to the urban communities. I know now that I think of it, many of the co-authors, the president of NEPAD, the New African Partnership for African Development, Ibrahim Moyaki, was one of the authors on that Bioenergy and African Transformation paper. I think the way they look at it, and I hope I'm getting this right, I'm doing my best to represent their view fairly. I think the way they view at it is there is no solution to poverty that doesn't include solutions for the rural poor. And you, in fact, need rural jobs so that the only place to get jobs isn't to go to the cities and live in slums. And there are job solutions that are specifically rural. There are job solutions that are specifically urban. And any coherent poverty-fighting policy would need to have a left and the right hand, as opposed to saying all of the progress will be in the urban areas and we'll just vacate the rural areas. I think that's a problematic scenario. So this is not the first complex issue we've discussed, and any answer I would give is incomplete, but that's my best attempt.
I know for developing countries, startup money is generally a problem. So going ahead and creating situations where they can go ahead and make the biofuel and do all the process in their country, where would they end up finding the funding if nobody's willing to go ahead and actually put any more than research into that?
Yes. Okay, so the question was, in essence, I think, in poor developing countries, where's the capital going to come from? Where's the investment? Am I oversimplifying, or is that?
That's pretty much it.
Okay. Yeah, this was the point I tried to wave my hands through to the end, at least my view of this point, which may not be the best. But the way I see it is this. If you restrict bioenergy or any other kind of development to projects that poor people can pay for, and you'd be surprised how prevalent that assumption is, then you have a tremendously limited range of things you can do. And in bioenergy, they're very, very well worked. For example, village-scale anaerobic digesters, wonderful technology, There are, I believe, over 1 million of them worldwide, and I'll bet Steve knows the number. No? Okay. Sorry to put you on the spot. No, there are tremendous numbers, not only in China, but, for example, in West Germany, or Germany, excuse me. So, was that the funniest remark of the day? Anyway. Okay, no, that was. All right. So, that technology is really, really well known. And it has its rates of propagation, and it's not capital limited, and it's not happening that much anymore. So, in the very early parts of the scale spectrum, where you need more money than you can find within the community, you're bringing it in from the outside. So you've got the Gates Foundation, the World Bank, you've got that sector, and they've done good things. They've also made mistakes, they would acknowledge. But you've also got private companies, going back to the business opportunity aspect of it. And I think that the greatest progress could be made with, especially since, as I mentioned, you very often don't have strong governmental structures where you would like to do these things. And if you have good government, it tends to be compartmentalized in ways that bioenergy works across. So development would be separate from agriculture, separate from energy, separate from environment. It's really hard. So I think thinking in the direction of there being a stakeholder for the non-monetized benefits from the beginning, and so that you can make autonomous governance without entirely having to depend on government, is the best answer I can give to avoid being limited to these very low. I mean, if you've got poverty, you don't have capital. And so I think you need to bring in outside capital. I think we'll go faster if some of that can be the private sector. But I think we can't rely on only the profit motive to get done what needs to be done. And I would love to see a project. What I think we need is experience with that model. I think there's the potential to go to the Gates Foundation, for example, and say, look, it's a reasonable hypothesis. We can get a lot of social development here. We don't want to screw some things up. Let's try to create some governance structures. Let's provide some insurance mechanisms, and let's measure what happens and start learning. I think that this is the train that the risks of inaction at today, in my opinion, are greater than the risks of action.
I think maybe we'll call it.
Fine.
Call it there.
Thank
That
you.
was great. Great way to end it. And Susan, they all have cars. I know.
Everybody,